All right, last topic in Unit 1 is the mole equation. Okay. Oh. Okay, so the mole equation, guys, it's a little tiny bit of math, but it's super easy, and we'll go over it in its entirety. But essentially what the idea of the mole is a way to express amounts of atoms or molecules. Because obviously atoms and molecules are something that are too small for us to see, okay, which makes them essentially impossible to count. So we have to have a better way of describing amounts of things, even if we're trying to actually describe how many molecules there might be for something. Okay, so the idea of the mole was developed for that purpose. Okay, so the idea of the mole is very similar to the idea of a dozen. Right? We all know that a dozen always represents how many? 12. Okay. Well, a mole always represents a specific number of atoms or molecules or whatever the particle is you're dealing with. Okay. In this case, it represents this many. Well, because remember, molecules and atoms are very, very small. Okay, I'm going to show you why they arrived at that number, how they arrived at that number in a minute, but that's the number. Okay, if I have 1 mole of something, I have that many of it. It doesn't matter what I have. If I have 1 mole, that's how many I have. Okay, so if I'm talking about water, that's how many molecules of water are in 1 mole. All right, if I'm talking about sodium, that's how many atoms of sodium are in 1 mole. All right, it's always the same, in the same way that if I have a dozen eggs, it's 12, and a dozen donuts is still 12. Okay, everybody follow there. All right, so the big things for today, guys, because we're basically just going to get through kind of explaining what the mole is today, because it's a short period. Okay, the mole is a unit for measuring the number of particles. Okay, and the relationship between mole's mass and molar mass is the mole equation. Okay, and the mole equation isn't like some long big thing that's like differential or whatever. It's easy. Okay, it's this: n equals little m over big M, which this formula highlights why chemists aren't in charge. Okay, because no self-respecting physicist would make an equation using 3 letters and use the same letter twice. Okay, and the only other letter used is one that sounds like the letter that was used twice. N and M, they sound a lot alike. This is why chemists aren't in charge and physicists are. I'm a physicist, that's why I say that. Okay, so we got n equals little m over big M, and we'll go over what each part of that means, but it's an easy formula to manipulate. However, I don't want to see any of these. Okay, I know that somewhere along the way, someone showed you this wonderful tool, and I am going to find out who they are, and I am going to kill them. Okay, because this does not teach you math. This is a crutch that I am kicking out from under you today. Okay, you will never use a triangle in my class, ever. Okay, you will not use it for right now, never. Okay, because it doesn't teach you how to do math. And here's the other thing: it only works if your equation has 3 variables in it. All right, this is like one of only 2 formulas you will use in Science 10 that has 3 variables. All the rest have 4 or more. And there's no triangle that works when you have more than 3. Okay, like for example, here's one that we'll use. Got a triangle for that one? There's no triangle for that one. Okay, or how about this one? No, I don't think you're going to get a triangle to work for that one either, because triangles suck. Okay? They just suck. And we're not going to use them anymore because we don't need them. We're all smart enough and good enough at algebra that we don't need a triangle. Okay, my rant on triangles is over now. Maybe. Okay. Oh, yes. Yes, it could be. I could be like that Walmart guy and just go off on a rant about triangles, but I won't. Okay, so the idea of the mole here, guys, is obviously there's more than one way to express the amount of things. And the most common way to express how much of something you have would be with mass. How many grams of it is there? Okay, another very common way could be volume. Right? How many milliliters or cubic centimeters or whatever of this material do we have? But sometimes it is useful to know approximately, at least, how many particles there are in a substance. Okay, that's the purpose of the mole. Right? If we saw a reaction take place between, let's say, one atom of sodium and one molecule of chlorine, would we even notice that reaction? No, it's incredibly small, and we can't see single atoms or molecules or anything like that, so we wouldn't notice it, right? We're always dealing with more than that many particles, which is why when we're balancing an equation, yeah, sure, we're putting in like there's 4 molecules of this and 2 atoms of that, but that could also mean there's 4 moles of this and 2 moles of that, okay? It's always a ratio, okay? Those balancing numbers we use are always a ratio. All right, so because we can't possibly count all of the particles, we use a representative number, in this case the mole, okay? And like we said before, it works the same as a dozen, okay? A dozen is always 12. It doesn't matter what you're talking about. It's a dozen always represents 12 of that, okay? Whereas for a mole, it's 6.02 times 10 to the 23 particles of a substance. Now, someone asked, how did they get that number? Here's how they got that number, okay? Using hydrogen, which is the simplest of all the atoms, okay? They took 1 gram of hydrogen and tried to figure out how many atoms there would be in that single gram, okay? By taking the approximate mass of a proton, approximate mass of an electron, and then figuring out how many would be in there. It was this many, okay? So then from there on out, all the atomic masses, that you see on the periodic table, that's the mass of this many atoms of that material. No, you couldn't necessarily, well, you could probably see it because there'd be enough of it there, okay? But it would have a mass, like if we're talking about potassium, for example, okay? If I had 1 mole, if I had that many atoms, 6.02 times 10 to the 23 atoms of potassium, it would have a mass of 39.09 grams. Okay, and if I had 1 mole of carbon, it would have a mass of 12 grams. So there would be enough to see. Okay, but certainly there would be. No, it's 10 to the power of 3. So really, this is 602 with 21 zeros behind it. Okay, it's a number in scientific notation. You guys done scientific notation before? Okay, let's talk about scientific notation then. Sorry, I took for granted that you'd already learned that because you were supposed to. Anyway, okay, so scientific notation is a way of representing a very large number with a much smaller number. Okay, our numbering system works on a base of 10. That is, each space in our, if we go up 1 space, it's a factor of 10 times bigger. Okay, no, well, that's the metric system. That's different. Okay, so let's say I have this number here. 123,450, well, that's a terrible 5. I don't know what happened there. 56. Okay, and let's say it's 0.78, just for argument's sake. All right. If I want to represent this number in scientific notation, I need the base of the number, that would be this part of it here, to be between 1 and 9.9. Okay, so it's always a number between 1 and essentially 10, but we never make it 10. All right, so how many spaces do I need to move the decimal in order to get a base that's between 1 and 10? All the way over to here, right? Okay, so that's going to be 1, 2, 3, 4, 5 spaces. Each one of these spaces is a factor of 10. So I would write this as 1.2345678 times 10 to the 5. Okay, that's the same number, right? Right, because if I multiply that by 10 to the power of 5, it's this number, right? Because I moved the decimal 10 spots. Everybody follow there? Okay, same goes if you have an incredibly small number. Okay, if I've got 0.00012345 and I want to put that into scientific notation, I need to move the decimal to the right. Okay, so that's going to be 1, 2, 3, 4, 5 spots. Okay, but now instead of being 10 to the 5, it's going to be 10 to the negative 5. Okay, so this will be 1.2345 times 10 to the negative 5. Okay, we just the exponent is how many spots did I have to move the decimal. Yeah. All right. Now, so that means that the mole number there is, like I said, 602 with 21 zeros behind it. So is it a big number? Yes. Okay. And again, it was arrived at through calculation, not counting. Right? To count to that number would take you maybe your lifetime. It's a big number. Okay? Like, it's certainly not somebody had a pair of tweezers and was picking atoms out, going like, okay, 458,928, 458,929. Damn it. 1, 2, right? I mean, if you lost count, you'd really be in trouble. Okay, so they didn't do that. Obviously, it was arrived at through calculation, not through any actual physical counting of the particles, because they're too small to see anyway. All right. Okay, so this number here, the guy who did this calculation, his name was Avogadro. Okay, so this is commonly referred to as Avogadro's number. Okay, the 6.02 times 10 to the 23 is Avogadro's number. It's not a number you're going to have to memorize. It'll always be given to you. Okay, I think it's on your formula sheet. A constant, yeah, Avogadro's number, Avogadro, same thing. Yeah. Okay. All right, now, when we're writing out things in moles, okay, we don't actually write the whole word because we're far too busy. Okay, so we abbreviate it as MOL to save ourselves 25% time on reducing one number down. Okay, because we're busy. We have an abbreviation for at. Right? At takes too long to write at. We have an abbreviation. We're busy. Actually, that's pretty neat. That's like one of my neatest ones ever. Yes, and I'm going to get to that, what each part of the equation represents, but N is the number of moles, little m is the mass in grams, and big M is the molar mass, which we haven't talked about yet. So, okay. The small m is mass in grams. Yeah, it does. Small m is on top, big M is on bottom. Okay, so the mass of 1 mole of a substance is called the substance's molar mass. If we're talking about things on the periodic table, which are atoms, it's called their atomic mass, but it's still their molar mass. Okay, it means the same thing. It's the mass of 6.02 times 10 to the 23 atoms of that material. Okay, if we're talking about a compound, then it's 6.02 times 10 to the 23 molecules of that compound. All right, but it's always whatever the smallest particle of that material is, that's the thing we're looking at. Okay, so for hydrogen, the molar mass is 1.01 grams per mole. Okay, that's what it says there on your periodic table. So if I wanted to calculate the molar mass of a compound, here's how I would do it. The example we have here is water. Okay, so if I write water as H2O, how many hydrogens are there in it? 2. Okay, so the molar mass of one hydrogen is 1.01. So I multiply it by 2, and then I add on to that the mass of oxygen, which is 16. Okay, so I should get that the mass of 1 mole of water, well, but on yours it's 16. I'm going by what your periodic table says. Right? Yeah, I know. Mine goes to far more decimals than your guys' does. Okay, always go with what your number says. Okay, all right, so if I had 6.02 times 10 to the 23 molecules of water, it would have a mass of 18.02 grams. In other words, it would be about 18 milliliters of water. Okay, is that very much? 18 mils is not very much, right? Like a can of pop is 355 mils, right? So 18 mils would be maybe enough to fill a couple of like bottle caps with water, okay, if you had like water bottles. No, not really. We're still saying these decimals here aren't being multiplied by many numbers. This is 22.989707 grams, right? Okay, only the 6.02 is being multiplied by the big number. Okay, does everyone kind of follow how I calculated that molar mass? That's something that we got to be able to do, because molar mass is not something you're going to use the mole equation to calculate. It's always something you're going to use your periodic table to calculate. All right, so you'll always have it. As long as they tell you what material you're dealing with, you can always calculate its molar mass using your periodic table. All right, so I want you guys to calculate the molar mass of the first two for right now. Okay, then we'll go over the first two and then we'll try the others. Okay, let's have a look at least the first one here. So in our first one here, we've got sodium chloride. So if I want to calculate the molar mass of sodium chloride, I have to take the molar masses or atomic masses of the things it's made up of. All right, so sodium is 22.99 grams per mole, and 1 chlorine is 35.45 grams per mole. Okay, so when we add those together, okay, we should get 58.44 grams per mole. Okay, and again, the units for molar mass are grams per mole because the mass of 1 mole. Okay. All right, for our second one here, we've got iron with bromine. Okay, so the molar mass of iron is 55.85 grams per mole. Okay, and bromine is 79.90. But how many bromines are there? 3. Okay. Now you don't need the brackets there. I'm just enclosing that so you know I'm not multiplying this number by 3. I'm only multiplying this one by 3. Okay. All right, so when we got that, we got 55.85 plus 79.9 times 3. All right, 295.55 grams per mole. All right, big. A gram, if you had a raisin's about a gram. Yeah, in terms of mass, yeah. All right, let's look at 3 and 4 here because I've had a number of questions on number 4. So for number 3 here, we've got phosphorus and we've got oxygen going together. So we got 30.97. Is that right? Okay, times 2 plus 16 times 5. Okay, so there's our 5 oxygens and our 2 phosphorus. Okay, so 30.97 times 2 plus 16 times 5. And it gives 141.94 grams per mole. What's that? Wabbit MU. It's an emulator. It's a TI-83 emulator. You have to have the code from your own TI-83 calculator, the ROM code. Sometimes you have to actually hook your calculator up. Like you can install the app and you hook your calculator up to the computer and it'll read it off of there. Yeah. Okay, so for the next one here, the trick here is that I've had a few people say, well, Mr. Cutter, what's the molar mass of ammonium? And the answer is, I don't know. You have to do it piece by piece. Okay, so this has to be done element by element in order to get the molar mass. So in this compound here, how many nitrogens do I have? 2. Right, I've got 2 ammoniums, that's 2 nitrogens. So I got 14.01 times 2. There's my nitrogens taken care of. How many hydrogens do I have? 8. Okay, so plus 1.01 times 8 plus 1 sulfur, which is 32.07. Okay, and then I've got 4 oxygens. Okay, so 16 times 4. All right, so I've got to add all of those together in order to get the molar mass. So we'll have 28.02 plus 8.08 plus 32.07 plus 48. No, not 48, 64. Yeah. Okay, so 132.17. Grams per mole. Okay, how important is it to remember to put units on an answer? Very important, okay? If you don't put units on an answer, it's just wrong. because I don't know whether it's apples, oranges, atoms, old ladies with walkers. I don't know. Okay, if it doesn't have units, I don't know what you're talking about. Which equation? I don't understand what you mean. Oh yeah, no, that's fine. However way, whichever way you want to do it. Yeah, that's fine. Mathematically, it's the same thing. Yeah. Okay, how many people have done the last one? Okay, I'll give you a minute here, and we'll go over the last one. All right. So for our last one here, we've got two scandiums, which are 44.96. Is that what it says on yours? Or say 95 on yours? 96? 96. Okay, and there are two of them. Okay, and then we have three carbonates. Okay, and that means that there are three carbons, so 12.01 times 3, okay, plus 9 oxygens, so 9 times 16. All right, put those together. So 44.96 times 2 plus 12.01 times 3 plus 9 times 16. That gives us 269.95 grams per mole. Okay. Calculating molar mass making sense to everybody? Okay, all right. So it's not too tough, right? Basically, you just got to look them up on the periodic table, add them up. Okay, pretty straightforward. All right. Now, when we're looking at a chemical equation, and I kind of alluded to this earlier, those coefficients, those balancing numbers that we've been putting in when we're balancing reactions, they can mean different things, okay? But they are a ratio, okay? They're saying that I need 3 times as many molecules of hydrogen as I do nitrogen in this reaction. Everybody follow there? Okay, and that'll produce, 2 times as many molecules of nitrogen trihydride as I started with over here, right? So things like that. It's still, what it's doing is it's conserving everything. It's making sure the mass on both sides is the same, okay? But it's also telling us ratios. So this could mean literally 1 molecule of nitrogen gas plus 3 molecules of hydrogen gas gives 2 molecules of ammonia. Or it could mean 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to give 2 moles of nitrogen trihydride or ammonia. Okay, it could be that as well, right? It's just telling us the ratios of everything. And the reason that this is important is because when you get to Chem 20, you're going to have to do what's called reaction stoichiometry, which is if you know how much product you had, you'd have to use these balancing numbers to figure out how much of each one of the reactants you had in terms of grams. Right? It's not something we do in Science 10, but it's what you'll move towards in Chem 20. Sorry. Not always, no, because like if I'm saying there's 3 times as much mass of hydrogen as there is nitrogen, that's not true because hydrogen's much lighter than this stuff, right? I need 3 times as many molecules or moles, right? Because for every molecule of nitrogen, I need 3 molecules of hydrogen, but I don't necessarily need 3 times as much mass because this stuff is so much lighter. Yeah. Okay, so it could look something like this. Okay, like we said, it could be 1 molecule, 3 molecules, 2 molecules. It could be 10 molecules, 30 molecules, and 20 molecules. It's just a ratio. Okay, it could be 1 mole or 3 moles or 2 moles. Okay, but when it gets to the mass part, okay, then it's not necessarily that I need 3 times as much mass of this. Okay, I need 28 grams of nitrogen, but I only need 6 grams of hydrogen because hydrogen's much lighter, right? But over here, I still end up with 34 grams, okay? 28 plus 6 is 34, and over here I still end up with 34 grams, right? Okay, so like we said here, the one way to look at it is in terms of particles, okay? The other way to look at it, oh, this is, that's Avogadro. He kind of looks like a mole, yeah. I think mostly it's the style of his suit. They had this weird cut of suits then with these funny high collars. Yeah, he's got the big eyes too. Anyway, okay. So we can't obviously count molecules. That's why Avogadro came up with his number. Okay. and that's why we use it. Okay, we said also that those coefficients could represent the number of moles. Okay, so we've already talked about that. Okay, and okay, that's the most important information that is provided, okay, by a balanced chemical reaction. All right, then we talked about mass as well. The numbers don't necessarily mean 3 times as much mass. Okay, the mass is calculated independently. All right, mole equation. N equals little m over big M. All right, so N represents the number of moles. Little m, which is on the top of the equation, represents the mass in grams. And big M, which is on the bottom, is molar mass in grams per mole. Okay, so N is the number of moles. Okay, M is the mass of the material, and that's in grams. Okay, and M, big M, is the molar mass of the material, which is in grams per mole. All right, a little bit of algebra for you here. Okay, algebra is easy. You only need to remember 3 rules, and actually in this unit you only need to remember 2 out of the 3. Okay, if I want to move something in an equation, what do? Okay, before I apply it to both sides. Like if I'm adding something on one side and I want to move it to the other, what do? Oh my. Okay. All right, so that's where we're going. Okay, right now I'm dividing by big M. If I want to move it to the other side, I have to multiply. Okay, so if I want to move something, this is rule number 1. If I want to move something in an equation, I do the opposite. Okay, so if I'm multiplying, I divide. Well, it's getting like swap and drop, and I was getting strange answers. That's why I got worried. Okay, all right. So if I want to move something, I do the opposite operation to move it. Okay, the second rule is what I do to one side, I do to the other, and that's all you need to remember to manipulate this equation. There is a third rule. Okay. You move what's not attached to what you're looking for first, but we won't need to deal with that till we get to physics. Okay? For right now, you just need to remember these 2 rules. If I want to move it, I do the opposite. What I do to one side, I do to the other. Okay? That's all we need to remember. So, for right now, if I wanted to not solve for N, but I wanted to solve for mass instead, okay, so the little black M here at the top, how would I get black M by itself? Right, okay, I would move big M, right? I just want to get this one by itself. I want to get black M by itself. The best thing to do would be to move big M over to this side, and so that it would be alone, right? Right now I'm dividing by big M, so I would multiply both sides by big M, okay? So in other words, it looks like this. I multiply both sides by big M, so there's a big M on the top and a big M on the bottom. Big M divided by big M is 1, right? So in other words, they cancel. Right? Then I do the same thing over here. Now black M is by itself. Big M times N equals little m. All right? Everybody good with that? Okay. You're not going to have to solve for big M using this equation, are you? Where do you always get molar mass, big M, from? From the periodic table. So you're never going to use this equation to solve for big M. That's really the only manipulation you're going to have to do. Okay? All right, so if I want to solve for little m, I just move big M over here. It is, except that I actually did the math here instead of covered up a number with my thumb and went, ooh, now it's this. Yeah, okay? So in that way, no, it's not the same. The reason I'm going over this is because you have to know the fundamentals of why this works so that you can apply them to a more complex formula. Okay? So like just looking at another formula here.